We started into this discussion of SQL by learning about relational algebra, and relational algebra being kind of an abstract representation of our SQL queries. So all of our relational algebra expressions can be evaluated or expressed in structured query language and vice versa. So we talked about two unary operators of selection and projection. Selection, which returns a subset of tuples based on some criteria, and projection, which returns a subset of attributes that we're interested in. And then we've talked about six binary operators, our three set theory operators of union, intersection, and difference. The join operation, which had the natural join, inner join, and then left, right, and full outer joins. Also the Cartesian product, which is the all possible combination of tuples from the two relations, which in and of itself is not that useful, but we did show that we could join or combine the Cartesian product with a selection operation to return only tuples from the Cartesian product where some evaluation of equality evaluates to true. And this winds up being very similar to our equijoin, or very similar to an inner join. So that is kind of a different way to get to the same ultimate output. And then division, we didn't really talk about a lot because that's one of these fringy things that we don't use a tremendous amount, but that's where we look for all tuples in one relation to be present in some subset of tuples in another relation. But I wouldn't worry too much about division at this point in time because, like I say, it's kind of a fringy thing. Our joins and our set theory operators and select and project, that's what we're really going to be doing quite a lot of in our normal day-to-day SQL interactions. So we operationalize these in our select from where block. And this is kind of the fundamental piece of writing SQL that pretty much everything else is going to build from, where we select some list of attributes, or we can say all attributes by saying select asterisk from some table, right? And a table is going to be a collection of attributes that together describe some entity, right? So a table might be something like students or employees, and that's a collection of attributes that describe a student or an employee or a course or a vehicle or a product or something like that, right? So we select some list of attributes from one or more tables where some condition is met. And this condition is going to be what the select operation is using to return a subset of tuples that match this Boolean condition. So we could say something like select asterisk from students if we wanted to return all attributes about all of our students. Or we could project a subset of attributes by saying select and then the list of attributes we want to project, like empid, fname, and lname, from employees, that's our table in this case, where this condition is true that the value of this attribute state is equal to, in this case, tx. So this would give us the employee ID, first name and last name of all our employees who have a value of texes for state. Okay, so this is just a pretty straightforward select statement. And then we could build on this using our group by, having, and order by expressions. So group by groups together rows based on some common value of whatever attribute we are grouping by. And this pretty much always goes along with our aggregate queries. So if we wanted to find, for example, the average salary of employees in a particular department, we could select the name of the department and then average salary, that's our aggregate query, from employees group by department. So finding employees that have a common value of department and then calculating the average salary of the employees in that department. Or in this example, we are grouping by a common value of the college attribute and returning the average number of hours for courses that are offered by that college. And this is one of the examples we had in a previous lecture. Having is very similar to where, except when we're evaluating the output of an aggregate function, we have to use having instead of where. Okay, so it's very similar, except this when we're using the output of an aggregate function in that evaluation. And then order by simply changes the order in which our tuples are returned. We looked at a
So,
number of,
Professor,
yes,
do you mind going back one slide real quick?
absolutely.
So, in terms of the averaging hours, like, so we say select college, average hours. Um, Even though like AVG open parentheses hours is not, it's not an attribute yet. It's still gonna like project on the table with an average score. It's gonna know to go to each. It's gonna average out the salaries. That's what I'm asking.
Yeah, it's going to average, well, in this case, hours, but I think I said
Yeah.
average salary. But yeah, so it's going to take all of the values of that salary attribute per a common value of whatever attribute we're grouping by, and it's going to calculate that average, and that's what's going to be returned. Okay, and this is basically like a derived attribute because it's something that we're calculating at the time that we're executing this query.
And one more thing, the output, like if you're grouping by college, would the output, it would be the number of tuples that there were colleges, right? Just from my understanding.
The number of tuples you're going to get in return would be equal to the number of distinct values for
For
college that you have.
colleges. Okay, great. Thank you.
Yep, no problem. And we're going to work through a couple of examples and SQL queries before we get into our ERQs, so that might help clear things up as well. So we've also talked about a number of comparison operators, some simple ones like greater than, less than, equal to, not equal to, things like that. So if we wanted to find all of our employees who have a salary greater than 50,000, our SQL query would look like this. Select asterisk, we're just getting all attributes, from employees where this Boolean condition evaluates to true the value of the salary attribute for that individual employee is greater than this value, 50,000. We could also have kind of more complex or fuzzy search operations using the like operator, which allows for wildcards. Okay, so this is really helpful if you're looking for something like all of your employees whose last name starts with the letter S or something like that. We could say select asterisk from employees where L name like S and then our wildcard character, which in Oracle and pretty much every other DBMS is the % sign. Now it's a little different in Access. We use an asterisk for any number of characters, or we can have just a single character wildcard, and that's the underscore in Oracle and most other DBMSs, or a question mark in Microsoft Access. Okay, so a query like this would allow us to find employees that have a first name that starts with some letter, then has an I, and then some other letter, and then an A. So this would match like Tina, Tina, or Gina, Gina, or Micah, Mica. Like all of these things would match this expression here. But it has to be exactly one character, an I, exactly one more character, and then an A. That's what this term here does. This G % sign would match the last name G, if someone's last name was just the letter G, or like George or Joseph or some, whatever. Anything that starts with a G and then has any number of characters, including no characters at all. And we can have a lot of kind of sophisticated patterns of underscores and % signs and do some really kind of powerful things using the like operator. So it's kind of a fun, cool thing to play around with. And then we also introduced this is operator, which is necessary when we are evaluating whether a value is null or not. Because null is the absence of any value at all. It's not a zero, it's not a blank space. It is saying that we don't know what this value is. And so the interesting thing about null is if you do an expression of equality, your null values will not be returned. And if you do an expression of inequality, your null values will not be returned. Okay? So you think of equal or not equal to as being the opposites of each other, and you should get kind of the inverse set of tuples returned. But if you have null values, they're not going to be returned by either one. So if you want to evaluate something and ask if it's null or if it's not null, we have to use the operator is or negate it by saying is not. Okay, so just another example of how null values kind of make our data a little bit more difficult to work with, and why we generally want to try to design our database to minimize the number of null values we're going to be dealing with. Yeah, and all can be negated with our not operator. All right, so here's the examples I promised, and we have 3 examples of kind of increasing complexity here. And so we have this little business requirement here. We want to run a SQL query that's going to show all attributes for employees with a salary greater than 20,000, and then order the results by last name. And now in this question, I'm not specifying what the name of the table is or what the name of the attributes are. So I'm just going to kind of make those up as we go. Typically on the exams, I will show you a table or show you some sample data and ask you to write the query based on that so that you do know exactly the name of the table and the attributes. But for this, we're just going to kind of play it by ear a little bit. So all of our SQL queries where we are reading data are going to start with select, and we want all the attributes. So we're just going to start with select asterisk. Okay, and then next we need to say from the name of the table. In this case, I'm guessing the table is just going to be called employees. So I'm going to say from employees. And then we have this condition that we only want our employees who have a salary greater than 20,000. So to do that, we're going to say where salary greater than 20,000. I don't see any aggregate function. I don't think we need any grouping. Since we're not doing any evaluation against the output of an aggregate function, we don't need a having statement, but we did want to order the results by last name. So we're going to say order by L name. And by default, order by is going to return the results in ascending order. So this is going to give us our employees whose last name starts with A first. So A, then B, then C, then D, and then on through the alphabet. If we wanted this to be in reverse alphabetical order, so starting with our employees who have a last name that starts with Z, then Y, then X, and so forth backwards down the alphabet, we would just add the keyword DESC after L name. So we would say order by L name, DESC for descending. But select asterisk from employees where salary greater than 20,000, order by L name. That's how we would write this query. Pretty straightforward. It's a fun example. Let's move on to fun example number 2. Here we want to list each department name and the department's average salary, so it sounds like an aggregate function coming up, for departments that have an average salary of 50,000 or above. Do not include the accounting or economics departments, and order the results alphabetically by department. Okay, now one thing that we have to keep in mind is that when we do a group by and when we use aggregate functions, we can only project attributes that we group by or the aggregate functions themselves. Okay, so what we want here is the name of the department and the department's average salary. Okay, so we're going to project only those two things. And we project that, and it's a little bit confusing, but what we're projecting comes right after the word select. Okay, so before we projected all of our attributes with select asterisk. Now we're going to project just the name of the department and this calculation of the department's average salary. So we're going to select department, comma, average salary. So this is our aggregate function from employees because we're calculating the employees' average salaries per department. Okay. So select department, average salary from employees. Now, our where, you might think at first that we could say where average salary greater than 50,000. But remember, we have to use having when we're making a comparison based on the result of an aggregate function. Okay, so that's not what we're doing right here. However, we do have a where condition we need to put in place because we say right here, do not include the accounting or economics departments. Okay, so where we're going to exclude this is right here. We're going to say where department not in this set of values, accounting and economics. Okay, so instead of this in, we also could say where department not equal accounting or department not equal economics. And it's weird, you have to use an or there with this inequality instead of an and, because think about this, there's never going to be a department whose name is not economics and accounting, right? Everything would evaluate to true. So that actually gets a little bit weird and tricky. It's a little bit more clear, I think, to say department not in this set of values, accounting and economics. Okay, so this is how we're excluding these two departments from this output. We need to group by having a common value of department because we're getting the average salary of each department. So we group by department. And then here's where we're going to get our departments that have an average salary of 50,000 or above. We're going to say having average salary greater than or equal to 50,000. And then we're ordering the results alphabetically by department, and that's in our order by clause, order by department. Okay, so this is going to give us the name of the department and the average salary of the department for all of our departments that have an average salary greater than or equal to 50,000, excluding the accounting and economics departments. So moving on to fun example number 3, kind of a similar question here. We want to list each department and the number of faculty members in that department that have a salary over $100,000 when the average salary in the department is less than $80,000. Okay, so we're going to have to find departments that have an average salary less than $80,000. And then for those departments, how many members of that department have a salary over $100,000? So who's getting paid a lot of money and or a lot more than the average salary of the department? And we're going to order the results so the department with the largest number of faculty meeting this criteria is first. Okay. So this time we want the name of the department and a count of the number of faculty members that have this salary over $100,000. So we're going to use a different aggregate function. We're going to use the count function. And here it doesn't specify this in the problem, but this is giving this an alias of num_faculty just to make the output a little bit prettier. So select department, count of imp ID, and we actually could just count asterisk here if we wanted to. Just a couple of different approaches we could take. So this is going to give us a count of the employees from employees. Where, now what's our where statement going to look like? So the $80,000, we're calculating the average salary of the department. So that's not what we're doing right here. What we're looking for are the number of faculty where the condition is true that their value of salary is greater than 100,000. So we're going to say where salary greater than 100,000. So this is getting rid of all of our faculty members that don't meet this criteria. We're going to group by some common value of this attribute department. And then here's where we're finding our departments that have an average salary less than 80,000, having average salary less than 80,000. Okay, so we have two aggregate functions here, right? We're one, counting the number of employees in the department that meet this criteria, but then this other aggregate function is finding the average salary of the department. Okay, and this is going to be of all employees, even those that have an average salary greater than 100,000, because our grouping happens before the where occurs. Okay, So this is going to give us all of our departments that have an average salary less than 80,000, and then we're ordering by the number of employees meeting this criteria in descending order. So we're going to get the department that has the most employees making over $100,000 when the average salary of the department is under $80,000. Okay? So when we're working through these queries, both in assignment 3 and in the SQL project, I would encourage you to kind of play around a little bit and make some changes to your queries and try to kind of predict how this is going to change the output, and see if you're right and see if you're wrong, because this looks a little bit complicated as we were talking through it, but the more you play with this, the more kind of second nature and the more this is going to make sense. So it's one of those things that practice really is going to be your friend here and make this a lot easier to do. But as we can see here, this becomes a pretty powerful language the more we use it. Recall that we talked about having aliases for tables. So we can specify a shorter name for a table, so we can refer to it later in our SQL query. So this can be a really useful shorthand, but also something that we are going to have to do if we are referring to the same table more than once in a query, as we do when we do the recursive queries and the unary relationships. So something to keep in mind there. We also talked about a number of different binary operations like our inner joins. So we would say something like select and then whatever attributes we want to project. In this case, it's just all of the attributes from one table, inner join another table on, and then whatever the joining attribute here is. And typically this would be a foreign key and a candidate key that the foreign key is referring to. We also talked about a couple of different ways of doing a natural join, but as I mentioned, and as I think you will come to find, just doing a equijoin or a regular inner join like this is going to give us a little bit more flexibility than a natural join without really, excuse me, without really giving up much in the way of functionality. So really, this normal equijoin, the inner join, or an outer join is going to be kind of your most useful tool for most cases. Now, if we are joining a table to itself, again, recall that we do have to use our table aliases in this case. So this is an example that we had in class last time where we had our table of employees, and each employee had an attribute of manager ID that described the employee ID of the employee that was an employee's manager. Okay, and that's how we established this unary or recursive relationship. And then we also talked about how we could join more than two tables together. And to do that, we actually have to join just two tables and then join the third table to the result of joining those first two tables. All of our joins are always going to be binary operations. They're always going to be between just two tables at a time. So in this case, we're joining two tables together, and then we join the third table to the result of those two tables being joined. And we also talked about this alternate approach where we could create the Cartesian product and then select from the Cartesian product only where this condition of equality is evaluated to true. So this is just two different approaches to getting the same result. We talked about how with an inner join, we only get in our result tuples where there is a matching tuple in the other relation. However, the outer join, whether it be a full left or right outer join, is going to return all tuples from one relation or the other or both, even if they don't have a matching tuple in the other relation. So in the example that we had in class, we showed how we had, I think, these 11 tuples that are returned by the inner join, And then this one tuple that would be returned by a left outer join where we have a department that doesn't have any courses, or this tuple that's returned by the right outer join where we have a course that doesn't have a department, or that both of these tuples that don't have a matching tuple in the other relation are returned in our full outer join. We also talked about set operations, where our two relations must be what we call union compatible, meaning they have the same number of attributes and that the pairs of attributes are from the same domain. So we showed how we do the union of two sets, the intersection of two sets, meaning tuples that are found in both relations, or the difference. And in Oracle, we use the operator minus, and in most other DBMSs, we use the operator except. So if you're using set theory operators, just keep that in mind. And in the SQL project, there are a few queries that specifically ask you to use a set theory operator. And there's a couple of questions that it's the same question repeated 2 or 3 times, but it asks you to use a set theory operator versus a subquery versus an outer join or something like that. So be on the lookout for that as you start working through the SQL project. We talked about subqueries, and we're almost through our review here, and we're going to be getting into the ERQ in just a couple of minutes. We talked about a couple of different types of subqueries, the most useful of which I think being the uncorrelated subquery, where we have one SQL query nested inside another. The inner query is going to execute and return some set of values that the outer query can evaluate against. And we typically use this with the in, any, or all operators, and we can negate that, of course, with our not operator. So in this example, we're selecting from the course relation where course number is in the set of values returned by this subquery, select course number from section. So this inner query is going to execute. It's going to return this set of values, and then the outer query is going to return the tuples where the value of course number is in this set of values that the inner query returned. Okay, so this is what's going to happen and what is going to be returned. And of course, all of our values for course number in the section relation must be found in the domain of values of course number in the course relation for this to work out, right? So this is really a foreign key relationship where course is the parent and section is the child, right? And this makes sense because we have a course like Business Analytics 6354, and there are one or more sections of that course. So there's one course that could have many sections, and that's what we're seeing demonstrated in this example here. And then we could use the any and all operators with these subqueries to, in addition to in, which is what we used here, okay? And so in the example we had in class, we had this subquery where we are selecting the value of salary for this department code 3, and then we wanted to select all of our faculty members that have a value of salary greater than all of these values of salary that are returned by this subquery, okay? And then we said that there are other ways we could do this, such as in our subquery, doing an aggregate function just to find the max salary, and then finding all of our professors that have a value of salary that is greater than this maximum, right? So here we returned all of these values and then found in our outer query all of our tuples where this expression evaluates to true. The value of salary is greater than all of these values that were returned. Or we could just return the single maximum salary and find in our outer query any tuples where the value of salary is greater than that one singular value. Okay, so it's just two different ways to get the same result. And we've seen this pattern kind of over and over again where we can, do this or that. We could use set theory operators or a join or our subquery. right? Or we could do a join, or we could do the Cartesian product and then select based on a condition of equality and get the same result. So the point here is there are often going to be many different ways to do the same thing. Sometimes it's not going to matter at all which you do. Sometimes it's going to be a lot easier to do one way or versus the other, right? So knowing more than one way can really save you from some sticky situations. Sometimes there's going to be performance differences doing things one way versus the other. So that's why I'm kind of trying to drill into you this idea of having different approaches and knowing different tools and techniques, even when it gets the same result. So much like we talked about when we were doing the entity relationship diagrams, decomposing our problem into smaller problems and then kind of putting together these smaller problems to make to answer our bigger question, we're doing the same thing with our SQL queries, right? So when we had our 3 fun examples and question 2 and then question 3, it kind of progressively got a little bit more complicated and a little bit more complicated. What we really had were a number of smaller problems that we needed to solve, and we just kind of put those smaller problems together. We need to find all of our employees that make over $100,000. Okay, we'll start by writing that SQL query. And then we need to find all of our departments that have an average salary less than $80,000. Okay, we'll write that query. And now take those 2 queries and kind of put them together to answer the bigger problem, right? We decompose things just like we do with anything else.